away we go. We had a long list of objectives, but the pieces that we had not covered out of those objectives had to do with secant and cosecant. And just before you get out of here, to kind of put it in the back of your mind, we talked about how secant of theta is 1 over the cosine of theta, and how we can just use the graph of cosine and at the very last second turn the graph upside down, because the characteristics of the secant function are inferred from the fact that it's the reciprocal of the cosine function. So when I look at this blue cosine graph up here, I see that, yep, we're going to have some asymptotes with this, because the zeros of cosine would have us dividing by 0. So what we have to do is think, what did we do when we graphed cosine before? And what we did was we said the period is 2 pi over b, and that was 2 pi over 1, which is 2 pi. And we broke that into fourths so that we could talk about those important increments. So each of these increments was going to be pi over 2. So let's get those on here. 1 pi over 2, 2 pi over 2 is pi, 3 pi over 2, and 4 pi over 2, which is 2 pi. And then backwards a little bit, so negative pi over 2, negative 2 pi over 2, which is negative pi. And then let's go ahead and put our 1 and our negative 1 on the graph. So to begin, you graph just as you would be graphing cosine. So you think about Kahala. Cosine starts high axis, low axis, high, and working backwards, follow the pattern. And now here's where it changes. Because anywhere that our cosine graph is on the x-axis, that means y is 0. That's where those are. And so what's happening there, if we flip this cosine graph over, is there's going to be asymptotes at those positions. So we'll change colors here and get some nice asymptotes. And now we're to the point I mentioned, where what we have to do is turn this graph upside down. So the normal way that we would make this into a nice smooth curve, we realize isn't going to work because of those asymptotes. And what happens is we use the points that were not on our x-axis to guide us and give us individual branches. Parabola branches that we have there for secant. So we've learned how to graph this already. The one thing we have to do is be very careful that we remember to turn it inside out. Unfortunately, sometimes students, you get so carried away with, oh, I'll just use cosine, and then you graph it as a cosine graph, which it's not. So take that extra second at the end to say, okay, this wasn't cosine, this was secant. So it's a series of parabolas that we have there. And when we analyze it, f of x equals the secant of x. The period, of course, is the same as when we were talking about cosine and sine, the sinusoids. Period equals 2 pi. We don't have any zeros because our little parabolas never get to that x-axis. Now our vertical asymptotes, if we take a look up there, we see they're negative pi over 2, pi over 2, 3 pi over 2, and so you try to find a way to describe what on earth is going on there. And the easy thing to do is say, you know what, the first smallest asymptote that I have that's positive is pi over 2, and between 3 pi over 2 and pi over 2, if we do a little subtraction there, we get 2 pi over 2, which is 1 pi. And we realize that's the spacing of the asymptotes. They're pi units apart. So we have, for the vertical asymptotes, x equals pi over 2 plus n pi, where n is the set of all integers. And that will make those vertical asymptotes show up where we need them. There are no horizontal asymptotes, and our domain, again, is just where the vertical asymptotes are, but with a very important, don't use those. Asymptotes, we're never going to get there. We approach, but we never touch. The range, that's a little different, because we notice that we have this big space between a y value of -1 and 1. And so when we talk about the range, we have to realize that it comes up from negative infinity, but then we're going to stop at -1, and -1 is obviously on our graph, so we need our square brackets. But we're not done, because as we move further up, the graph begins again at 1, so square brackets, and goes up forever. So we have to make sure we've got those arrows on there to accurately show everything that's taking place. Continuity, again, we say it's continuous on its domain, so that anybody studying this graph would say, oh, yeah, not the asymptotes. That's not going to work. The vertical asymptotes are not part of the graph. Symmetry. This is an even function, and you can see that right here. That's going to be an even function. And then you think about how all of this would reflect over the y-axis, and you've got it. So if it's even, secant, like cosine, means that we could have a negative in front of the x, but because it's even, we drop it. And that's excellent, you know, being able to drop a reflection that we would have to think about and deal with. So even functions, cosine, and secant. Local extrema. Well, we do have local maxes and local mins up here. So we have to take a look and realize that these are local mins, and these are local maxes. So it says we have a minimum of 1. Yes, we do. And where did that occur? That occurred at 0 and at 2 pi. So given how symmetric this is, we know that that's going to space out every 2 pi because that's the period. And so we would say the minimum of 1 is at x equals 2 pi n, where again n is the set of all integers. And then we look at -1, and we see that we have it at -pi and at pi, and we realize the space between those is of course 2 pi because that's the period. So we'd start with the first nice positive one, which would be 1 pi, and we say x equals pi plus 2n pi, where n is the set of all integers. Now this is not bounded above or below because our graphs obviously have arrows that show we're going up and down forever, except for the gap between our -1 and our 1. So kahala for secant, and at the last second, switch it and make it little parabolas. Cosecant, same thing. We want to think of cosecant of theta as 1 over the sine of theta. So what we're going to do is we're going to graph the sine of theta, and at the last minute, turn it upside down. So when I'm looking at the sine of theta, I'm looking for where sine is going to be a 0. Because that's where my asymptotes are going to take place. I'm going to be dividing by 0 at 0, pi, 2 pi, etc. So when I graph cosecant, I get into my head, hey, this is sine, and 2 pi over absolute value of b would be 2 pi over 1. So it's 2 pi, and I need a fourth of that 2 pi. So again, it's going to be 2 pi over 4, which is pi over 2. So let's go ahead and get those increments on there. So 1 pi over 2, 2 pi over 2 is pi, 3 pi over 2, and then 4 pi over 2 is 2 pi. And let's go to the left a little bit here too. And on our y-axis, we want to have +1 and -1. Then we want to focus on what we know about sine. Sine was sahala. So sine was axis, high, axis, low, axis. Follow the pattern backwards. And now what we need to do is say, okay, where are the asymptotes? Well, pretty obvious from our graph. Where we have the points on the x-axis is what we're looking for. So we'll go ahead and put those asymptotes on. Any of those points that have a y value of 0, because 1 over 0 will be undefined. And then we turn it inside out, upside down. I should have used blue to make that stand out. Let me cut that. Let's put our parabolas in here. Hey, no new learning, Cedarholm. Yeah, that's the beauty of knowing the sine graph and the cosine graph so well. You know, all we have to do is at the last minute turn it upside down, inside out. There it is. So now our analysis for f of x equals the cosecant of x. Period is still going to be 2 pi, and again, if it's not the parent function, 2 pi over the absolute value of b. We don't get any intercepts. It's not crossing the x-axis. Our vertical asymptotes are at negative pi, 0, pi, 2 pi, so we start to realize, oh, that would be easiest if we just say it's the set of all x such that x equals n pi, where n is the set of all integers, because those are the multiples of pi that we have up there. Horizontal asymptote, don't get one. Domain, well, use the vertical asymptotes, but say don't use these. That's our domain. And then again, our range, we've got a big hole in our graph between y values of -1 and 1, so we have to make sure that we use that negative infinity to -1 with square brackets, union 4, and we've got 1 with square brackets to infinity. Continuous on its domain, and the symmetry for this one is odd. And of course it is, because sine has odd symmetry, so cosecant will also have odd symmetry. And that means we can't get rid of the negatives. We can move them, and we're definitely going to do that. If we see a negative attached to our b value in here, we're going to move that out in front, because it's easier to deal with there, and we won't forget it. Local extrema, well, that's going to be at these positions. So our minimum of 1 up there, and that occurred at pi over 2, and of course we know that the period for this graph is 2 pi. So we'll have pi over 2, and then we'll have to add 2 pi n, or 2n pi, where n is a set of all integers. And then for our maximum of -1, we're at negative pi over 2 and 3 pi over 2. So once again, if we take 3 pi over 2 minus a negative pi over 2, we'll see that we have 4 pi over 2, which is 2 pi. So negative pi over 2 plus 2 pi n. Now, I've been showing you how to write these using the smallest positive that we have. Notice this one has the negative. It would not be wrong to say 3 pi over 2 plus 2n pi. N is the set of all integers. There are a lot of different ways to write that. And so if we stick with the smallest positive, we would use the 3 pi over 2 plus 2 pi n. Not bounded above or below, so there it is. Cosecant is sine upside down. Now, we have to sketch at least 2 cycles of the graphs of the following equations, and again, you want to immediately be looking at this and thinking, okay, don't forget that this is cosecant, but cosecant is what we get from taking the reciprocal of sine. So let me see if I can fit my little one up there. Probably not. There. All right, so 1 over the sine of theta. I'll have to write smaller. There we go. So that means I have to graph this as if it were a sine curve. And so I'm looking at this, and I see that I have a negative with my b value. So I think about sine and how sine has odd symmetry, and I realize, well, I can't just make it disappear, but I certainly could move it out in front. And I don't like that 0.5. I would much rather work with 1/2. So I'm going to change that to 1/2. Cosecant 2x minus 1. So now we want to think of that negative 1/2 and remember what that does. And so this is a reflection over the x-axis. So reflect over the x-axis. That 1/2 is a vertical compression. Factor of 1/2. And while I'm thinking about that, I think, well, you know what, I probably better put some space here for my y's then. And maybe go every 2 blocks as a 1. Like so. Because while I'm doing that, I'm thinking about that vertical shift that we have in the back as well. So let's keep going. We've got the vertical compression of 1/2, and then we have the 2, which is a horizontal compression. Factor of 1/2. And then the -1 in the back is, of course, a vertical shift. Down 1. All right. So let me go ahead and put my helper on here, which is my vertical shift of down 1. And now we start the heavy lifting. So normally, period's 2 pi over b. If this were just sine, then it would be 2 pi. But we did have a b value of 2. So this will be 2 pi over 2, which is 1 pi. And I start thinking about my intervals, and I realize I have to take 1/4 of that. So 1/4 of pi would be pi over 4. So putting that in the box to remember that that's what I should use for intervals. But I'd really like to know that starting and stopping point for one period of this graph. And we're back to using 0 to 2 pi. But in the middle, well, we have a 2x. Again, don't go all the way back up to the black one. Use the first red one that's up there. This is going to be 2x. Divide everything by 2. And we have from 0 to pi, starting and stopping. We know our increments are pi over 4. We're probably not going to write all that down. We're just going to go ahead and say this is 1 pi over 4, 2 pi over 4, 3 pi over 4. So I'm going to go ahead and space by 2's here. 2 blocks. 1 pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, and 4 pi over 4, which is pi, 5 pi over 4, and 6 pi over 4, which reduces to 3 pi over 2. And then let's go backwards to the negatives if I can make out where my vertical lines are. There's so much fading. Negative pi over 4, negative pi over 2, negative 3 pi over 4, negative 5 pi, sorry, missed my pi, negative 4 pi over 4, negative pi, negative 5 pi over 4, negative 6 pi over 4, which is negative 3 pi over 2. All right, so now we know that sine usually starts at 0. Well, this one had a vertical shift of down 1, so we're going to have to start here. Sine is axis high normally, but this one, we've got a negative in the front. We have a reflection. So with that reflection, instead of going axis high, we're going to have to take those highs and make them go low. And in fact, we have to make them go low by 1/2 a unit. So there is our next point. So we have axis, then we have low, axis, high, axis, low, axis, high. So we're going 1/2 a unit above and below. And again, you're going to have to follow the pattern. And then remember that anything that falls on the x-axis, well, it's not the x-axis this time, it's the line y equals -1. Anything that falls on there gives us an asymptote. So I'm going to change colors and get my asymptotes on here. Try and get that blue to disappear. There we go. So we're going to be able to graph a lot of little parabolas. Oh, I missed an interval there. Got flustered when the phone rang. Leave me alone, I'm making a video. There we go. All right, let's turn it upside down. So all of these points that are not on our new axis of y equals 1 get turned away from the axis. So that's why I say it looks like it's been turned inside out. Wow, look at that. We've got it. So again, it wasn't new. All the graphing that we did was graphing that we've always done before. The difference is we have to turn it inside out when we get done. So we sketched at least 2 cycles of the graphs of the following equations. And one of the things that I'd like to add to this is, let's try and figure out what we could write for the vertical asymptote. So our vertical asymptotes from the left, negative pi over 2, negative pi, I started out with negative 3 pi over 2, negative pi over 2, 0, pi over 2, pi, and 3 pi over 2. So the smallest positive of those, set of all x, such that x equals, smallest positive would be pi over 2. And then we need to think about what's the width between those asymptotes. And from 0 to pi over 2 is obviously pi over 2. So we want to go by pi over 2's each time. And to get that to happen each time, we have to put an n up there in the numerator and say this is for n, which is the set of all integers, and finish it up with one of our number set brackets. So yeah, that's a skill we have to learn. We have to be able to write those. I know so far we were just looking at them, and we had our basic analysis for cosecant and secant graphs, but that's a skill. So we should put that, at least let's do these two, where we're talking about how do you write your own vertical asymptotes. Alrighty, looking at B. Y equals 2 secant negative pi over 2x plus pi. So the first thing that I see is it's secant. And I remember, oh yeah, secant, that's 1 over cosine of theta. There's a negative in there for B. I'm going to factor that out and think about what I can do with that. All right, so factoring that out, taking the negative out of both of those. And then I realize, wait a second, cosine, that's the even one. I don't need that negative. Excellent, I'll just drop it. Pi over 2x minus pi. Well, then, of course, we see that that little pi over 2 is our b value in there, so we'd better factor that out before we can talk about all of those transformations. And pulling out that pi over 2, just think of how you could get all of that back to pi. So we'd need a 2 in our numerator, so the 2's would cancel. Freaky, Cedar Home. Look at that. An x minus 2 in there. Yeah, it happens. You've seen some pretty strange ones in your homework, too. So y equals 2 secant of the quantity pi over 2 times the quantity x minus 2. Now let's talk about those transformations. We have a vertical stretch factor of 2. we have a b value there of pi over 2. Well, you better figure out what pi over 2 is, because if pi over 2 ends up being a number that's bigger than 1, then we're talking about a horizontal compression. And if it's a number that's less than 1, well, then we're talking about a horizontal stretch. And 3.14 blobity-hoo divided by pi, that's going to be more than 1. So this is a horizontal compression. Factor of the reciprocal of pi over 2. Which is 2 over pi. Won't that be interesting? And then we have that little 2 in there for h. So we have a horizontal shift 2 units to the right, since that x is so naughty. Always the opposite of what we see. All right, there is no vertical shift. So I take a look at my a value in front, and I think, probably better just go by 1s again on my y's. And we need to figure out what we're going to do for intervals here. So secant cosine, period is 2 pi, over the absolute value of b, and our b value was pi over 2. So we are going to have to multiply by the reciprocal. And this just feels weird. The pi's drop out. And we get 4. Well, let's see our inequality, because a fourth of 4 is 1. So we're going to be able to go by 1s on the x-axis? Well, secant 0 to 2 pi, just like cosine, and we have pi over 2x minus pi. So let's see what happens here. We'll add pi to all 3 pieces, and then we'll have to multiply all 3 pieces by 2 over pi. All right. Ooh, cool. Our pi's drop out there. That's just an x. And our pi's drop out in the last one, and we have 3 times 2, which is 6. Strange, but that'll be really nice. That means we can go by 1s for our x's. But I am going to stretch it out a little bit. Maybe go every 2 blocks is a 1. If I can make out where the 2 blocks are. And back. So like I said, we had some interesting cosine and sine graphs that you all had to do before. Now, with this one, we do have a phase shift. So let's put a little helper on at our phase shift here. And that phase shift was 2 to the right. So we don't forget that that's our new starting point. And now let's try to put it all together here. So this is going to be our cosine graph. And cosine starts high. We took that negative out of the picture because this is even. So we're going to start high. And where we have to start high is going to be where that phase shift is. And we have to go up 2. So now, cosine, kahala, high axis, down to low axis, high. Follow the pattern backwards. Anywhere that we have a point that's on the x-axis is going to be an asymptote. So I probably don't want to use my black because that's my phase shift, but it is part of the asymptote, and I only have limited colors here. I have 3 of them, so I'm going to go ahead and use that so that we can see what's going on. So there's a 0 and another. And now we have to turn it inside out. Upside down. Looking like so. So very nice secant graph there that had a lot of things going on. So now what we want to do is try to write our own vertical asymptote. Number set notation. So vertical asymptote, set of all x such that x equals, well, let's take a look. We have asymptotes at -5, -3, -1, 1, 3, 5, etc. So the smallest one that we have there would be a 1. And then we figure out, well, how far away are we talking for each one of these? And you can see from any of those that that's going to be 2 units. So we will need to add 2n, where n is a set of all integers. So 1 plus 2 times 1 would be 3. 1 plus 2 times 2 would be 5. And if we go backwards and put in a -1 in there, 1 plus 2 times -1 is going to be -2. We get our -1. All of those pieces in there. Except you always think, well, what's going on at 0? Well, 0 we already know. You know, if we put a 0 in for 2n, it's going to be at 1. So it works. You kind of go through it and make sure, do I have everything that I need here to get people to land on those vertical asymptotes? And we have it. So at this point, you may be kind of like, we did so much graphing. We're only going to do 1 cosecant and 1 secant? Yes, because we've done so much of the sinusoids already. We should be super good at those. Now, as we start on example 5, 6, and 7, we're looking at more of the, hey, we're giving you a little puzzle. Let's see if you can figure this out. Solving a trigonometric equation algebraically. Find a value of x between pi and 3 pi over 2. So the first thing I'm doing is thinking, let's figure out where between pi and 3 pi over 2 is. That solves to give you the secant of -2. So I think of this as -2 over 1, and I realize, well, that's a 30, 60, 90. It has to be. So that's the only one that has 1, 2, and the square root of 3 in it. And then secant is what we get when we flip cosine. So this is hypotenuse over adjacent. Let's start putting our labels on here. So the hypotenuse is 2. And our adjacent here, get that blue to turn off, our adjacent here would be a 1. But we know that this is 1 unit to the left, so that's going to be negative. And we also know that the other side of this triangle is going to be a negative square root of 3, because we have to go down with that. So across from the square root of 3, that would be a 60-degree angle. So we think about 60 degrees and realize that's pi over 3, because pi is 180. And I have to come up with the name of that angle coming from the positive x-axis all the way around to that terminal side. So I'll have to do pi plus pi over 3, little common denominator action. And it's 4 pi over 3. So there's our value of x. Now, they specifically stated that we have to be between pi and 3 pi over 2, which means we have to give that in radians. For you tries, and it's been a little while since we did these, but I would encourage you to pause the video and try it yourself, and then watch the solution, and then pause the video again and do B and see what you can do. So we want to make a drawing. Trig is so visual. And we see that this one asks us to use x values between pi and pi over 2. That's here, so we're in second quadrant. And it says the cosecant of x is 2, but again, we know that was 2 over 1. So we're starting to get a feel for that 30, 60, 90 triangle again. Cosecant is what we get when we flip sign. So that's hypotenuse over opposite. Let's get our reference triangle in there. And this needed to be x this time. They're not using theta. And we know the hypotenuse is 2. We know that opposite is 1. And yeah, it would be positive because that would be going up 1. But down here, we would have a negative square root of 3. What we needed to know was the 1 is opposite our angle of x in that corner. And that means this is a 30-degree angle. So then we think, well, 180 degrees divided by 30, we're talking about pi over 6 for that little angle. But we're going to have to go from the positive x-axis, so we'll go all the way over here to the terminal side. We'll have to leave out that pi over 6. So 1 pi minus pi over 6, go ahead and get your common denominator, and yeah, you probably already did this in your head, which is good, and that's 5 pi over 6. And we have it. So like it says, you follow their directions. Solve for x in the given interval. You should be able to find these numbers without a calculator using reference triangles in the proper quadrants. Absolutely. Absolutely. All right. So again, pause, try to do B, and then start it up again. For B, we are supposed to find where the cotangent of x equals 1, and it says we need to be between negative pi over 2 and negative pi. That's third quadrant. Drawing my reference triangle, putting a little x in there, and I start thinking, cotangent, huh? Cotangent is what you get when you flip tangent. Tangent is opposite over adjacent, so this is going to be adjacent over opposite, and it has to be 1 over 1. I need 2 1s in my triangle. Ooh, I know that one. That's a 45, 45, 90. So opposite over adjacent, those would both be negative in the third quadrant. So negative 1 divided by negative 1, or adjacent over opposite if you want to think in terms of the secondary trig function, which is cotangent. And then what we'd have to do is realize, well, the hypotenuse is square root of 2, but we really don't need that, because while we were thinking about what those sides were, we realized that across from x, that's got to be a 45-degree angle. Has to be. It's the only way this is going to work. So now we have to give them a name, but they were very specific. They said we have to give a negative name for this angle, and it has to be between negative pi over 2 and negative pi. So this time we have to think backwards and see, okay, what would that be for that terminal side right there? Well, what we're doing is we're going all the way over to negative pi, but we have to leave out our little 45 degrees, which is pi over 4. So 1 pi minus pi over 4. Again, you probably already did this one in your head. 4 pi over 4 minus 1 pi over 4 is 3 pi over 4, and we have to slap a negative in front of that because they were very specific about how we had to name that. And we have it. Now, this last one we're going to have to use a graphing calculator for. So I'm going to pause here and get my graphing calculator working. Example 7 says solving a trigonometric equation graphically. So big help there. They're telling us we're going to have to grab the graphing calculator. Find the smallest positive number x such that x squared equals the cosecant of x. Now, we're not at the point where we could solve this algebraically yet, which means, yeah, we have to grab the calculator. So we're going to have to put one side in as y sub 1 and the other in as y sub 2, but then you remember, hey, there's no cosecant button on my calculator. Nope, we're going to have to put in 1 over the sine of x in order to get our graphing calculator to understand that we want cosecant. So let's take a peek. Y equals x squared, and then parentheses 1 divided by the sine of x. And let's quick go into mode and make sure we're in radians, which we are. Window. Let's go with 2 pi. So 2 second pi. And we'll have to make that bigger, then we make it bigger. That's just how it is. And we want to be able to see that x squared graph, so maybe we'll go to 10. There it is. So here's what they wanted. The smallest positive number, such that x squared equals the cosecant of x. Well, Blinky's sleeping under second trace. Blinky's been taking a long nap here. Blinky the pet cursor. We'll go to intersect number 5, and wowzers. That was not the smallest number, not the smallest x value. I need to get Blinky down here where the smallest x value would be. Enter, enter, enter. So there it is. Our x value is 1.068 to 3 decimal positions. There it is. That meets all of our lovely objectives that we had for section 4.5. Graph tangent, cotangent, secant, and cosecant functions. Graph transformations of tangent, cotangent, secant, and cosecant functions. Use tangent, cotangent, secant, and cosecant models to solve problems. And you might say, these didn't look a lot like word problems. And that's okay. You know, we're working that way. We're trying to get there. We have a lot of understanding that we have to do to get to that point. I just decided I'm not going to move ahead into the next section. There's a really big visual for that I want everybody to understand, so that would be better to wait until I have some students in the classroom and on the Google Meet on Monday. So now you can do 4.5 day 2 and 4.5 day 3. Remember what I was talking about in class. You know, you do have the weekend for this, but if it gets to be a little bit much, I tend to stretch those due dates out a couple of days when we end up in this situation. It happens. Nothing we can do about it. So have a great weekend, everybody.